As we look at this animation of our planet from NASA, we see that more of our surface is covered with water in the form of oceans than land. We can also see a lot of water vapor in the atmosphere. Water is why our planet has life. Water as a substance is incredibly important in oceanography, and also to our planet as a whole. Here are some learning outcomes that you can come back to after the lesson is over to make sure that you can do all the outcomes listed here. We take water for granted because we've been observing it in our daily lives forever. But in reality, water is a really strange substance that does some things that are chemically kind of weird. Let's start with the chemical nature of water itself. Even though many people are not particularly fond of chemistry class, almost anyone can give you the chemical formula for water, H2O. Water is composed of 3 atoms, making it a molecule. The molecule is composed of an oxygen atom and 2 hydrogen atoms. Atoms are composed of a nucleus of protons and neutrons and outer rings of negatively charged electrons that orbit the nucleus. The inner ring can accommodate 2 electrons, and the second ring can accommodate 8. If the second ring is not completely full, atoms may share electrons, which then orbit both nuclei. This bonds them together, forming a covalent bond and causing a molecule to form. In the case of the water molecule, oxygen has a bigger nucleus than hydrogen does. So the shared electrons spend more time orbiting the oxygen nucleus and less time orbiting the hydrogen nuclei. Electrons carry a negative charge, so the extra time they spend with the oxygen gives it a slightly negative charge, leaving the 2 hydrogens slightly positive. Because one end of the water molecule is slightly positive and the other is slightly negative, water molecules are attracted to each other, sort of like magnets. The negative end tends to stick to the positive end of another water molecule, forming a weak bond that is not a true chemical bond. These hydrogen bonds are much weaker than the very strong covalent bonds that cause the water molecule to form in the first place. Do you have a water bottle sitting on your desk? If so, the water molecules in it are constantly forming and breaking these hydrogen bonds as we work through this lesson. Because of this polarity, meaning one end is different than the other, and the resulting weak hydrogen bonds, water molecules constantly bond together. This property is known as cohesion, meaning that the molecules like to stick together. Water, like most liquids, looks very structureless, but in fact, water has more structure within it than many other liquids have because of its cohesion. One really evident manifestation of water's cohesion can be seen in its surface tension. If you try really carefully, you can get a paper clip to float on a glass of water as shown in this picture. The reason you can do this is because water forms a surface that resists being stretched or penetrated. This is unusual for liquids, and even for water the surface tension is relatively weak. Try the paper clip trick to see what I mean. It's really tricky. The surface tension is because water forms a weak membrane on its surface. Why does it do that? Well, remember cohesion. Water molecules like to stick together, forming hydrogen bonds. Within your water bottle, the molecules are constantly forming and breaking bonds with each other in all directions. But at the very surface, the water molecules can only bond with the molecules below or beside them, not above them, because there aren't any. So the bonds they make with the fewer molecules around them are more concentrated, and that is what creates the membrane that gives water surface tension. But water molecules also like to stick to other substances, which we call adhesion. Look at this picture of water droplets on a window pane. This is something we've observed all of our lives, yet you've probably never stopped to think about what is going on here. Why does the water form droplets? The droplets form because water has cohesion. The water molecules like to stick together, so they bundle up to form water droplets. But water flows downhill due to gravity, right? So why do the droplets stay on the window? We know that if the droplets get big enough, they will roll down the window, as some already have. But the smaller ones stay put, because the attraction between the water and the window surface is greater than gravity, up to a point. So water is attracted to other substances. This explains one of the key facts that most people know about the ocean. It's salty. After the chemical formula for water, probably the second most widely known chemical formula is table salt, NaCl. Sodium, the chemical abbreviation Na, by itself has a positive charge, while chlorine, Cl, has a negative charge. In your salt shaker, they form a molecule in a solid because the positive sodium bonds with the negative chlorine. But in water, salt quickly dissolves because the water molecules, with their polarity, are also attracted to both the sodium and the chlorine. The negative oxygen ends of the water molecule are attracted to the sodium, and the positive hydrogen ends are attracted to the negative chlorine. The water molecules surround these charged atoms, known as ions, and keep them from interacting and bonding together to make a solid salt. Lots of other substances besides salt will dissolve in water in the same way. Think Kool-Aid. For this reason, we refer to water as the universal solvent. Ocean water has lots of dissolved salt in it, but it is rare for even fresh water to be completely pure. Most water, including your drinking water, has at least some substances dissolved in it. We've tossed around the word salt without really defining it, but salt is a broader word than its use as table salt would indicate. A salt is a substance that forms from a positive ion and a negative ion bonding together to neutralize each other. So table salt is one, but we can also get KCl, potassium plus chlorine, and many more. Ocean water contains many positive and negative ions that stay dissolved because of the polar nature of the water molecule. We all know that water can exist at a range of temperatures. It can be very cold or very hot, yet most of us would be hard-pressed to define what we mean by heat or hot. So let's talk about these concepts as it relates to water in the ocean. Remember that water molecules are constantly bonding with each other and also breaking those bonds. That is because the water molecules are constantly moving. The movement represents energy. The more the molecules are moving, the more energy there is. The temperature of water is a measure of how much movement energy, which we call kinetic energy, there is in the body of water. As we look at these pictures, try to determine which of these substances has the highest kinetic energy. In which picture are the water molecules moving the fastest? I'll count slowly to 5 silently to give you time to pause the video if you'd like to take some time to think before I explain the answer to the practice problem. Pictures show A, an ice cube, B, a pool of water, and C, steam coming out of a geyser. So we have water as a solid, a liquid, and a steam. We know intuitively that steam is really hot. Steam is hot. It has a high temperature because it has a high kinetic energy. The water molecules are moving around really, really fast compared to the liquid water in the ice cube. The solid ice cube looks like water molecules probably aren't moving at all. That is actually incorrect. Even in the ice cube, there is kinetic energy, just much less so than in the liquid water or the steam. That brings us to our next related concept, which is heat. Heat is the total amount of kinetic energy in a body of water. So on the left, we have a pan of water about to boil, and on the right, a swimming pool. The water in the pot is very hot. The water in the swimming pool is pleasantly cool. But there's only a small amount of water in the pot, and there's a vast amount of water in the pool. So if we added up all the kinetic energy stored in the pool, because it's so much water, even though it's cooler, there's a lot more heat stored in the pool overall than in the pot of boiling water. So let's apply these two concepts. On the right, we have a glacier entering the ocean, and on the left, we have a geyser erupting with steam. You probably don't need to pause to answer the question, which is hotter, which has the higher temperature? Clearly, the steam and hot water droplets coming out of the geyser would be much hotter than the glacier and the cold ocean around it. But which of these scenarios contains the most heat? It may be counterintuitive, but the glacier contains much more heat than the geyser because it's much, much bigger, containing a lot more water. We know ice is cold, so it's hard to imagine that it contains any heat at all. But, as I discussed with the ice cube a minute ago, even in the ice, the water molecules are moving around a little bit, and that kinetic energy is heat. So while ice may not contain a lot of heat by volume, when you have a lot of ice, as here, that ice represents a lot of heat. One of the really neat things about our planet is that it is at the right range of temperatures that water can exist in all three of what we call its physical states. I took this picture in Iceland at a place where a glacier was breaking up as it was entering the ocean. The beach was littered with many icebergs that had washed up. It was a cold day, cold enough that the little icebergs were melting very, very slowly. But it wasn't so cold that the ocean was freezing solid. It was a cloudy day, and I could see clouds of water droplets in the sky. The clouds had formed from water vapor, a gas that is in the atmosphere. In the water cycle on our planet, water moves between these three physical states as it moves from place to place. So how does water move from one state to another? We're really familiar with these pathways from our everyday life. Ice can melt as solid water turns to liquid water. Why does it do that? It does that because we've added heat, which increases the kinetic movement of the water molecules within the body of water. Calories are measurement units of heat. In this diagram, we are considering what can happen to a gram of water. If we have a 1 gram ice cube and we want to melt it, we have to add heat, 80 calories worth. Note that the melting temperature of ice is 0. While we are adding the heat, before the ice melts, The temperature stays at 0 until we've added the 80 calories, and then it melts. Similarly, if we wanted to freeze water, we'd have to subtract 80 calories of heat at 0 degrees before it would freeze into ice. But what if the water we wanted to freeze wasn't at 0? What if it were at 50 degrees? We'd have to subtract 50 calories to get it down to 0, then subtract 80 more calories to get it to freeze to a solid. We can think of the pathway from liquid to gas, or water vapor, in the same way. So what does this have to do with oceanography? Another way to look at this diagram is to think about what is happening to the environment when these changes are happening. When we go from left to right on this diagram, we are adding heat to the water, which is removing heat from the environment. While if we go right to left, gas to liquid, or liquid to solid, we are removing heat from the water, which puts heat into the environment. The change from liquid to gas, or from gas to liquid, is especially dramatic. It requires 540 calories to be added to get liquid to boil or turn to gas, and it takes 540 calories to be subtracted to get water vapor to condense to liquid. The amount of energy that must be added or subtracted to bring about a change of state while the temperature remains constant is called the latent heat, and water has a remarkably high latent heat of vaporization. It takes a lot of energy to get water to go from liquid to gas. So here's an example. It's a hot day and the water is evaporating from a lake. What does that do to the water that is left behind in the lake? Pause the video if you would like to think about it. It takes a lot of heat to make the liquid water turn into water vapor, so some of the energy is being taken from the water, meaning that the water left in the lake may then be cooler. Here's another practice problem. Let's assume that all 4 scenarios shown here involve the same amount of water. Which process involves subtracting the most heat? First of all, we are looking for processes that involve subtracting heat, so we are looking for processes that involve cooling. So we can eliminate C, boiling water. Using ice cubes to cool water, B transfers the heat from the water to the melting of the ice cubes, so that process involves warming, even though it leaves the water in the glass cooler as the ice cubes warm up. A and D both involve cooling, but remember that the calories involved for a gas to solid change are much greater than that for a liquid to solid change, so D requires removing more calories than A. Let's imagine ourselves in this scene. It's a really hot day. Would you walk across this patio barefoot? Would you dive into this pool? You'd probably say no to the first and yes to the second. The warm sun will make the patio unbearably hot, yet seems to have little effect on the pool full of water. Specific heat is a term that refers to a substance's ability to change temperature as it gives up or takes in heat. Water, unlike the patio, does not change its temperature readily, so we would say that the water has a higher specific heat than the bricks of the patio do. In fact, water has the highest specific heat of all common substances. Here we are looking at a Google Earth image that shows us the average surface temperature for the land and the ocean. We see a range of both from very warm, red on land, light pink in the ocean, to cool, blue on land and in the ocean. But the difference between the coldest land and the warmest land is quite large, while in the ocean there is much less difference between the coldest ocean and the warmest ocean. The ocean, because it changes temperature more slowly than land, is more uniform. And that is really important. Without water, Earth would be just a big rock moving through space, kind of like Mars, shown here, which has no oceans and very little water. Rocks change temperature easily. They heat up in the sunshine and cool down rapidly in the dark. So if Earth were just a big rock, daily and seasonal temperature changes would be much more dramatic than they are on our own, mostly water-covered planet. Let's move on to a couple more interesting aspects of water, its density and its viscosity. Again, we'll talk about what these words mean and how these qualities apply to the ocean. Like many terms we use in oceanography, density is one you probably already know. As we look at the sponge on the left and the glass egg on the right, you can probably already answer the question, which is more dense. The glass egg is more dense, but it would be a mistake to think that it was more dense because it is heavier. Density is not the same as weight exactly. It is the mass, or weight, per unit of volume. So if we had a cube of sponge that was the same size as a cube of glass, the glass would weigh more, or have more mass. Therefore, it is more dense. But if you had a really huge sponge, maybe the size of a Volkswagen, it might be heavier than the glass egg in the picture, but it would still be less dense. We know that the ocean is very deep, especially in some places. At great depths, the pressure of all the water is very high, like an elephant standing on a postage stamp. Some substances change their volume and therefore their density with increased pressure. Imagine the elephant standing on the sponge. The sponge's volume would be greatly decreased as the elephant squished it or compressed it. Because it would now be so small, its overall density would increase. But water does not compress easily. Water in the deepest part of the ocean is only slightly more dense than the water in the shallow part of the ocean. So while animals that live in the deep parts of the ocean must deal with really high water pressures, they don't have to deal with water that is noticeably denser than water in the more shallow parts of the ocean. Water doesn't easily change its density with pressure changes, but it does change density with temperature. Before we interpret this rather complicated-looking diagram, let's think about what we already know about this from real life. Here's a practice problem. As we examine the picture, which is more dense, liquid water or solid water? Pause the video if you need to think about it. This is a situation that we encounter all the time. Ice cubes float on ice water because the liquid form of water is denser than the frozen solid form. So in this diagram, the x-axis, the horizontal one, is temperature, and the y, or vertical axis, is density. The bigger the number, the more dense the water is. The dark blue line represents ice as solid, while the light blue line represents liquid water. So if we start the lower left corner of the graph, we have ice that is about -4 in temperature and slightly more than 0.9172 grams per cubic centimeter in density. As we move to the right, the temperature warms as we add heat. As we add heat, we increase the kinetic energy of the water molecules. Because they are moving more, they are further apart, and the density decreases to about 0.9170 at 0 degrees. However, notice that when we add enough calories to change the ice to a liquid, 80 calories to be exact, the density suddenly increases dramatically to just over 0.9998 grams per cubic centimeter. In fact, the increase is so dramatic that we have to have a break on the y-axis, shown in gray, to make it even fit. Once the water turns to a liquid at 0 degrees, as we continue to add heat, notice that the density continues to increase until we get to just under 4 degrees on the x-axis, 3.98 degrees C to be exact. After that point, as we continue to add heat, the greater kinetic energy of the water molecules causes them to stay further apart, decreasing the density of water. Okay, so both ice and liquid water warmer than 3.98 degrees C become less dense as you add heat. So why is it that ice, with less kinetic energy per volume, is less dense than liquid water, which has more kinetic energy per volume? Even within liquid water, a certain number of molecules have bonded together, as we have discussed. But in liquid water, the bonds are random and disorganized, and the water molecules can fit tightly together. When liquid water turns to solid water, the molecules start to bond in a much more organized way, forming a three-dimensional lattice, as shown on the right. Notice that this organized structure includes more empty space than we see in the disorganized jumble to the left, representing liquid water. This organized structure with more space is the reason solid water is less dense than liquid. This is why ice floats, be it ice cubes in your glass of water or icebergs in the ocean. This chemical property of water is what brought down the Titanic. Alright, let's try to apply some of the concepts we've learned thus far in this lesson. We'll be doing some similar problems in class. Read the scenario and then pick the best possible explanation for it from the list. As you wipe the water off the pan, the water that was not absorbed by the dishcloth formed beads. Why did it do that? Why didn't it form a thin, uniform layer? The answer here is 4. Water molecules like to bond with one another, exhibiting cohesion, even more than they like to bond with other substances like the pan, the property that we call adhesion. The water molecules are pulled together into droplets or beads as they bond. Answers 1 and 2 involve changing temperature, which was not mentioned in the scenario. Answer number 3 is also a correct statement about water, but does not apply to this scenario. Viscosity is another term that you probably already know, even before I define it. Technically, viscosity is resistance to motion or internal friction, but we could think of it in terms of pouring a liquid out of a glass or a jar. We know the milk will pour much more easily than the honey. The honey has a high viscosity. It resists pouring out of the jar. If we toss something into the milk, maybe a cookie, it would easily sink into the milk. If we toss a cookie into the jar of honey, it would probably remain on the top because of the honey's viscosity. Water has different viscosities at different temperatures. It is more viscous when cold and less viscous when warm. The difference isn't nearly as great as the difference between honey and milk, but does make a difference to some of the smallest things that live in the ocean. Plankton are organisms that float in the ocean. Most of them are very tiny. It is easy for them to float and not sink when the water is cold and viscous. Many of them are photosynthetic, like plants on land, and can be detected by satellites in space. The map to the right shows us concentrations of these plankton in the ocean. Red and yellow colors indicate lots of plankton, while blue and purple colors indicate very few. Notice that the plankton are more abundant near the north and south poles, where the water is cold, than they are anywhere else. The viscosity of the water is not the only reason plankton are abundant near the poles, but it's certainly a contributing factor. Before we wrap up, here's another practice problem. We talked about how cold water is more viscous than hot water, but we didn't discuss the reason. Using the knowledge of the water molecule that you have gained in this lesson, you should be able to determine this for yourself. I'll give you a moment to hit pause if you need to think about it. Remember that temperature is a measurement of kinetic energy. So in hot water, the water molecules are moving around a lot, whereas in cold water, less so. Also remember that water molecules constantly form hydrogen bonds with each other. So in which body of water would you expect to find more bonds, which is what gives water internal structure? The viscosity is a reflection of this internal structure, and in cold water we'd expect more bonds and more internal structure. We've learned a lot about water, and here's a summary of some of the key points. Review each of the statements and make sure that you understand them and can apply them. In class we will do an exercise where we will apply these concepts to situations involving water in everyday life. If you go back to review, be sure to follow the embedded hyperlinks in the accompanying PowerPoint for more information and review. Thanks for listening.